Le Chatelier principle tells us that if a dynamic equilibrium, if a chemical equilibrium is disturbed by changing the conditions of that reaction, the position of that equilibrium will move to try to partially to reverse the change that we have introduced. So when we introduce, when we disturb the chemical equilibrium, when we introduce something that disturbs the position of the equilibrium, the reaction will react in a way to try to compensate and reverse those changes we have introduced. So when we're looking at chemical reactions, what could disturb a chemical equilibrium? Well, there are a few things we can play with. We can play with the concentration of the reagents of the products. We can play with the temperature to which the reaction takes place, and we can play with the volume of the vessel, or the pressure of the different, the pressure of the reaction in which the reaction is taking place. We can use Le Chatelier's principle for reactions that are in equilibrium to improve the product yield, because although the reaction will go back to the equilibrium state, in the process of going back to the equilibrium state, it will hopefully, depending on how the changes we introduce, produce more product. So the equilibrium constant will be the same, because that's the proportion of products to reagents, but the individual concentrations of each of the products and reagents will change just in an appropriate way, so the ratio of products to reagents stays constant for that particular, which would be the equilibrium constant for that particular reaction. Let's use the example of the Haber process, the production of ammonia from nitrogen and hydrogen, to see how playing with the concentration of reagents or products would affect the equilibrium. If we add hydrogen, which is one of the reagents, to the reaction, then the reverse reaction will not be affected, but the forward reaction will increase because there is more hydrogen, and the reaction will try to counteract that addition by making that hydrogen react, by consuming that hydrogen and go back to the equilibrium position. So the forward reaction will increase more than the rate of the reverse reaction until the equilibrium is again reached and the reaction stays at equilibrium. On the other hand, if hydrogen, one of the reagents, is removed, then we have the opposite effect. The reverse reaction will stay as it is, and the forward reaction will decrease. The forward reaction rate will decrease because hydrogen has been removed, and again until a point in which the equilibrium is reached, and the reaction rate will, the equilibrium is reached, and the reaction will stay at equilibrium. Playing with pressure and volume only has an effect when the reaction has gases, so some of the reagents and products must be gas, and when we have a different number of moles of gas in the reagent side and the product side. So if none of the reagents are gases, or if we have the same number of moles of gas in the reagents and the product side, then there is no effect. If there is a difference, then decreasing the volume or increasing the temperature, because remember that volume and temperature are inversely related, will move the reaction towards the side that occupies less space with a lower number of gaseous moles. So an increase in the pressure, a decrease in the volume, for example, a decrease in the size of the reaction vessel, will mean that the reaction will move towards the side of the reaction that has the lower number of moles in gas phase. Temperature has a profound effect in most reactions, and one of the most effective things you can do to speed up a reaction. First of all, increasing the temperature typically increases the reaction rate, so the equilibrium is attained faster. Also, temperature changes the equilibrium constant, and the equilibrium constants are only constant at particular temperatures. When the temperature changes, the equilibrium constant will change. How to play with temperature when you have a reaction in equilibrium? Well, you have here, for example, the reaction of CO2 and carbon to produce carbon monoxide, and this reaction has a positive enthalpy. So this reaction is endothermic. An endothermic reaction means that heat needs to be applied for the reaction to happen. Heat is a reagent. So an increase in temperature will mean adding one of the reagents to the equation, in this case heat, which will mean that the forward rate will be higher than the backward rate, the reverse rate, and it will move the position of the equilibrium, so forward. So increasing temperature in an endothermic reaction means adding one of the reagents and shifting the equilibrium towards the formation of the products. What is the effect of catalyst in the equilibrium? Well, the answer is they don't have an effect. Catalysts increase the rate of reaction, and they affect the speed to which the equilibrium is achieved, which is the final state for that reversible reaction. In the presence of a catalyst, because you are reducing the amount of activation energy that the reaction is by providing an alternative reaction pathways, the equilibrium will be achieved faster in the presence of a catalyst. Once a reaction is at equilibrium, catalysts have no effect, because the reaction has already started, the reaction is already at equilibrium. So they do not have an effect on the position of the equilibrium, they do not have an effect in the equilibrium. Simply, the reaction will achieve the equilibrium state at faster than if it had been an uncatalyzed reaction. So I'm going to ask you to stop the video now and try to fill in this table. Look at these different options that you might have to affect to disturb the equilibrium. Look whether they would have an effect in the equilibrium constant, yes or no, and also see what effects they would have in the equilibrium. Would it shift them right, forward towards the production of products, or left, reverse, backwards, towards the side of the reagents? So stop the video now, please. So I hope you had a go at the filling in the table. The easiest one to tackle with is the effect of all these changes in the equilibrium constant, and the only one that has an effect in the equilibrium constant is increasing the temperature, because the equilibrium constant is dependent, well, for a particular reaction, is dependent on the temperature. And there are different values for Kc at different temperatures. It does not have, the other changes don't have an effect on Kc. Many of them have an effect on the equilibrium. If you increase the concentration of reagent or decrease the concentration of products, the equilibrium will shift right. If you increase the concentration of the reagents, the reaction will react to consume those reagents in produced products. And if you decrease the concentration of products, one or more, by removing that product, for example, from the reaction vessel, then again the reaction will try to counteract that change by producing more product. Changes in pressure or volume affect the reaction when there is a different number of gaseous moles in the reagent and the product side. So if you do have that and you decrease the pressure or increase the volume, for example, you could decrease the pressure by having a larger reaction vessel, then there is more space. The reaction will shift in the direction of increased number of moles, whichever it is, reagent or product. If you increase the temperature and you have an endothermic reaction, then in an endothermic reaction, heat is a reagent. So increasing the temperature is providing one of the reagents, heat. The reaction will react to counteract that and will shift towards the right. And the effect will be the other way around if the reaction were exothermic, because in exothermic reactions, heat is a product. Increasing the temperature would mean that you're increasing one of the products, the equilibrium will shift left. And finally, adding a catalyst does not have an effect on the equilibrium. It speeds up the reaction and it reaches the equilibrium position sooner, but once the reaction is at equilibrium, adding a catalyst has no effect. In the previous examples of reactions in which you calculated and I asked you to write equilibrium constants, all the reagents and the products were gases. But in many cases, we have what we call heterogeneous equilibrium, in which you have a mixture of solids, liquids, and gases in your reagents and products. The equilibrium constant is written without the concentrations of pure solids or liquids. Solids and liquids are incompressible. You cannot, just applying pressure to them does not make them reduce their volume, which you have with gases. So their concentrations at a given temperature are constant. So for example, in this example, Kc would be written, I would depend solely on the concentration of hydrogen and the concentration of water, because those are the only two of the chemicals involved in this reaction that are gases. You will explore this in more detail in physical chemistry, introduction to physical chemistry and thermodynamics, but just quickly mention, because you might come across this in your reading, that when you have multiple reactions, so several reactions that add up to a final reaction, in this case, for example, two reactions that add up to give a third reaction, the equilibrium constant of that third reaction is the product of the equilibrium constants of the first two. So you might want to keep that in mind and you might come across this in your reading. So this is the end of the series of videos dedicated to chemical equilibrium. I hope they were useful. As usual, if you have any questions, just drop me an email and organize a tutorial with me. And thank you very much for watching.